Hey, Calc students, it's time for another FRQ. Today we are looking at the test from the year 2012, and we are looking at question number 3. And as you notice the question, you right away can conclude they gave you the graph of a derivative, and so this falls under the category of derivative graph style questions. So if we can just combine what we know about integration with what we know about the geometry of the graph, that's usually what they're looking for on these. So let's see what we're given and see if we can put this all together. So here's the graph they give you, and it is going from -4 to +3. And we have line segments and semicircles, which is not uncommon for these types of questions. And sometimes it's helpful that when you get these to go ahead and fill in some information. And just even filling in the x-axis can be helpful. And you see this, well, that was -4. -3, -2, -1. This is +1. This is 2. This is 3. And along the vertical axis, we have 1, 2, and 3. And that can be helpful sometimes. And we're going to be calculating some areas as well as we go. So let's see what it says. It says, let f be the continuous function defined from -4 to +3, whose graph, consisting of 3 line segments and a semicircle, centered at the origin, is given above, or to the right here. Let g be the function given by g of x is equal to the integral of 1 to x of f of t dt. Well, you have to, if you don't recognize this, you're pretty much stuck. But here's what's given. G of x is equal to the integral from 1 to x of f of t dt. Well, I'm going to show you this just a little bit different, and in fact it's probably easier to see if I just take the g of x and I'm going to put it over here instead. And so in case it doesn't jump out at you, which really it needs to jump out at you, is that we should all know that as a result of integrating, there's a special relationship between what you get after you integrate and its relationship to what was in the integral. Well, this right here, this is the derivative. It has to be. It's the derivative of that. In fact, we frequently write this down. We say the integral from a to b when we do the fundamental theorem, if I use f prime notation, the integral of f prime of x dx is equal to the original function f of b minus f of a. Sometimes we make this f and we make this capital F, but the relationship is known that this, what's inside my integral, is the derivative of the result, and that's how we check our answer. Well, that's really important for this question, because what they're saying, and they're just doing this to try to make it difficult, what they're saying is f is the derivative of g. And so, because that's true, you immediately need to recognize that, and on your picture you want to say, oh, this is the graph of f? Well, f is the derivative of g, so what I'm going to do is just remind myself of that and say, well, that's really g prime. So I've got the graph of a derivative, and I got to manipulate it. So what do they do to make it just a little more difficult? Make it a separate letter and call it f, and it just is going to throw some students. And it just makes it one more thing you got to kind of notice. So we've got that taken care of, and now let's proceed. It says find the values of g of 2 and g of -2. Well, this is a typical type of a question for a derivative graph. What they like to do is ask you to find by the fundamental theorem here the result. And so actually what I'm going to do right now is I'm going to replace this f right here. I'm going to replace that with g prime. Okay, so the integral of g prime, because they're the same thing, is g of x here. So what I'm going to do is I'm going to integrate with geometry g prime, and that's going to produce g, and we're going to see if we can put 2 in the answer. Well, I want to rewrite what they have up here, and what they have is the integral from 1 to x, and because these are the same, just because I think it's easier to follow, I'm going to put g prime of t dt is equal to g of x minus g of 1. So this needs to make sense when you see that, and you just go, oh, of course, it's the fundamental theorem. I'm integrating g prime, and I get this. Why am I using g prime? Because they're the same thing, and this is easier to see. So what they want you to do is figure out what is g of 2. So what I'm going to do in here is replace these with 2's. And I'm going to say, oh, well, I guess I'm integrating from 1 to 2, g prime, and if you want, you can make this x again or t, it doesn't really matter. That's really not a big deal. G prime of x dx is going to equal g of 2 minus g of 1. Okay? So we're going to use geometry to figure this out, because integration is area under the curve, and we're going to set these equal, and it wants us to figure out what is the value of g of 2. Okay? So let's go ahead and figure this out. We are going to, for this question, because we're isolating g of 2, I'm going to add over g of 1 to the problem. So I'm going to take this and move this over here. And I'm going to say, well, this is actually whatever g of 1 is, that's going to give me the integral from 1 to 2 of g prime, or sorry, the plus sign, plus the integral here of g prime of x dx, and that is going to equal g of 2. Okay? Now there's one little thing they're doing here that this may be the first time this has come up. If this was normally what they would be saying is that they would be giving you what g of 1 is equal to. But they're not going to do that for right now, and I'm going to explain why here after we calculate this. So let's see what we've got here, looking at our picture. And so our picture says we are going from 1 to 2. So if we look at the picture here from 1 to 2, this isn't the most convenient little regions here to calculate, because it's this little area right here. It's this little right triangle, which is kind of small. But it is a right triangle, and if you said, well, the area of this little guy right here, if you were just looking at that, you'd say, well, I know the area of a triangle is equal to 1/2 the base times the height. Well, this distance right here is 1, and this distance right here is 1/2. Now the reason I know that's 1/2 is because the slope of the line is 1/2. I would go over 2 and down 1. It's negative 1/2 is my slope. So if the slope is negative 1/2, I go over 1, down 1/2. So this distance is 1/2, this distance is 1, and so the area of this would equal 1/2 the base, which horizontally would be 1, times the height, which would be a negative 1/2. And I'm below the x-axis, so what I wind up getting here for the area of that little triangle would be negative 1/4. So the area of this little triangle right here, kind of weird, but the area of that triangle is equal to negative 1/4. So it would look like, right here, we would get this integral, or the area of g of 2, or I want to go back up to here. The area from 1 to 2, going through here, this would equal negative 1/4. Okay? Now we have to reconcile this issue of g of negative 1, and we have to, because this is unusual the way you would see this. Now, most of the time, you get this fundamental type of fundamental theorem of calculus type equation, and I want you to look up here, and I'm going to show you how this has just a little bit of a curveball that can throw you. I want you to look at the original statement in the question, and I'm going to write that again down here and show you just a little thing to notice. The original question says g of x is equal to the integral from 1 to x of f of t dt. Now this was given. So there's something implied here that makes this a little bit weird. And here's what it would be. If this is what is given, what you would be used to seeing is this. You would look at this and you would say, well, the integral from 1 to x of f of t dt, if I was going to do the fundamental theorem, I would just evaluate this as, since f is g prime, I'm going to go back here, I'm going to make this g prime again. So I've set this up above, but I'm going to say it in a little different context now. You would say, well, if I integrate that using the fundamental theorem, this should be g of x minus g of 1. Fundamental theorem, and then I'm just going to take this and if I bring this over here, this is what I want to show you, is that if I solve for g of x by bringing this over here, like I did up above, I'm going to write g of x first. And so this winds up equaling g of x is equal to, I'm going to add that over, but I'm going to write this on the other side of the equation. This would equal g of 1 plus the integral of 1 to x of g prime of t dt. So what most students do is when they look at this, they're like, I don't understand why this doesn't have g prime of 1. And it's a really good question, because you're probably anticipating fundamental theorem 2 pieces. Well, sometimes here's what happens. In this question, it's defined like this. And so there's something that's implied. And here's what's implied. It's implied that if this is what g of x is equal to, the reason they don't put g of 1 on there is that it must have been 0. And so it wasn't relevant. So if you're looking at this step right here, where you said, I just did the geometry, I know it's negative 1/4, but I just need to now put, I put g of 1 over here. I need to figure out the initial condition, or not initial, but I need to figure out g of 1 and add it to my integral. Because most students are like, well, I got the negative 1/4, that's the integral, so now I just need g of 1. And so what's peculiar about this question is that you don't need g of 1. I'm going to go back to this definition here, I'm going to write it a little bit different, and they wanted you to find out in the question g of 2. So I'm going to erase that and put a 2 there. I'm going to erase this and put a 2 here, and I'm going to show you that by definition g of 2 is just the area between 1 and 2 under the curve. And now I'm going to knock that off, and we already figured it out, and it equals negative 1/4. Okay? So what was the curveball in part A? The curveball was, for every kid that was thinking, I'm going to do the fundamental theorem from A to B, and I'm going to integrate f prime of x dx, and I'm going to get f of A minus f of B. Or sorry, f of B minus f of A. Every kid that was thinking this, unless you've seen this question, you weren't prepared for the fact that they defined it that this value was going to be 0. And so f of b, which for this case was a 2, didn't need this value, and so you might be sitting there going, it's negative 1/4 plus g of 1, but it's not given, and you're thinking I did something wrong. You didn't. So tuck this one away, that by definition, you wound up not having to do the other part of the fundamental theorem. Small little wrinkle on this, not a huge deal, but it definitely could be confusing if you haven't seen it before. So now that I've sort of shown it this way, just for the sake of space, I'm going to clean this up a little bit and get rid of some stuff. And I'm gonna not do the entire thing over again, but I'm going to write the setup a little bit differently, because I wrote it this way knowing that's what you'd be anticipating. So let me get rid of this. And I'm going to go back to the original and now just clean it up. So for part A, we already know the answer here, but now I'm going to start over. So for part A, it says find g of 2. Here's how easy this could have been. You would have said, oh, well, g of x is equal to the integral of 1 to x of f of t dt. Okay, what do they want? G of 2. Okay, so g of 2 is equal to the integral from 1 to 2 of f of x, but I'm going to make that g prime of x dx. You could leave it t's if you want, doesn't matter. Okay, so then you go over to your graph and you integrate by geometry from 1 to 2, and you figured out that, oh, that was equal to negative 1/4. Done. That's g of 2. Next one, they want to know what is g of negative 2. Well, since we've already discussed why this little one is slightly different than a typical fundamental theorem, g of negative 2 is just defined as the same way. We have to go from 1 to negative 2 of g prime of x dx. Okay? Now, the first thing you need to notice on this one, I'm going to draw a little line just to separate these two questions. And this was our answer up here to the first one. The first thing you need to notice here is A always has to be less than B. 1 needs to be less than negative 2, and it's not. Or this is your A value, this is your B. So we need to switch those around. Well, in order to switch those around, you just have to put a negative in front. So, and that's a completely legal adjustment here. So what I'm going to do is say, okay, well, g of negative 2 is equal to, I'm going to put a negative out front, and I'm going to move the negative 2 here and the 1 up here. G prime of x dx. Now we're okay, and now we're going to go back to our picture. So in our picture, now we have to integrate from negative 1 to 2 or negative 2 to 1 by geometry, but we have to make our answer negative. So let's take a look at the picture. And so we have negative 2 to positive 1. Well, it looks like from -2, looks like we have this long, skinny right triangle right there. And then we have this semicircle down here, which is below the x-axis, so that's going to be negative. So we've got that, and we have this right here we're going to have to figure out. Very reasonable, I think we can do that. Okay, let's do the triangle first. 1/2 the base times the height. Well, the base is 1, the height is 3. So 1 times 3 is 3 over 2. Right here, this area is equal to 3/2. Okay, and that is positive because it's above the x-axis. Over here, this is a semicircle. Well, the radius here is 1. So I know that the area of a circle is equal to pi r squared. My radius is 1, so the area of the circle would just be pi. But I have half of a circle, so I'm going to move this over here. So the area of the semicircle, so I'm going to put SC, is equal to pi over 2. And the semicircle is below the x-axis, so I know that this is going to be a negative pi over 2. So I'm going to put that inside here and circle it. That's a negative pi over 2. Okay? So here's what I know back on here. The integral from -2 to 1, I know that it's going to equal. I better have a negative out front, and then I'm going to come over here and say, well, I had my triangle up top, which was 3/2, and I had to subtract my semicircle on the bottom, which was pi over 2. But I had my negative out front, so I could just switch those around. So my answer would be, I guess I could actually write it as a common denominator, but I'm just going to go pi minus 3 over 2 is going to be that one. Okay, so geometry with integration, fundamental theorem with a little bit of a wrinkle because of the way it was defined. And so don't let that second little part of the fundamental theorem that's missing, don't let that throw you. It's not a huge deal. It just implies that it was 0. Let's look at B. B says, for each g prime of -3 and g double prime, or the second derivative, and -3, find the value or state that it does not exist. Okay, well, let's find g prime of 3. Well, g prime of 3 is pretty easy, because g prime of 3, we have the graph. And as long as it's at a decent location, we should be able to read the graph. Because g prime of 3 is the same as f of 3. So let's just go to the graph and find it. So it looks like, that's -3, not +3. So let's just go to -3 on the graph. So over here is -3, and right there, it's the middle of this line segment. That's annoying. So I guess we better figure out what's the slope of this line segment. So it looks like we went over 2. We'd go over 2 to here, and we would rise 2. It looks like the rise over run looks like it's 2 over 2. So it looks like the slope of that line is 1. So I'm just going to write that m is equal to 1. So if the slope is 1, and I was at -4, 1, I can just come back 1 and go up 1. So I'd be at -3, so that would mean I would rise to 2. So it looks like it just equals 2. Just reading a graph. I guess we could go back to middle school for this one. Pretty easy one. Okay, and now it says let's find the second derivative. So the second derivative at -3 would equal the first derivative at -3, not that that matters. But here's a little derivative stuff now, because we know that if the derivative is the slope of the tangent, but if the function is linear, it's the slope of the line. I'm going to say that again. The slope of the derivative is the slope of the tangent. But if the function is linear, it's just the slope of the line, because the tangent is the line. And we actually already calculated it. We got the slope as 1. So we needed to figure out the y value at -3 for the first part, and then we had to find the slope at that point for the second part, and the slope is actually equal to 1. And that is B. Okay, let's move on to part C. So part C says, find the x-coordinate of each point at which the graph of G has a horizontal tangent line. Okay, time for short review, and I'm going to draw using the colors. I want to review this concept here. This is, for the test, if you can have your notes, you want to have this here. So I'm going to draw this and then erase it. So there's my x-axis. And I'm going to draw a nice friendly cubic, and that's my original function. And I am going to switch to red. I'm going to take a red marker, and I'm going to draw my derivative here. And I'm going to handcuff the peak and valley. knowing that that is where my derivative is equal to 0. Okay, so my original function is increasing, the graph of my derivative is positive. The original function is decreasing, the graph of my derivative has to be negative. The original function is increasing, the graph of the derivative needs to be positive. Positive. So what you guys want to notice is when I have horizontal tangents, if I have a horizontal tangent at my peak and my valley, it means my derivative has an x-intercept. Very important. Now, if I want to keep going and do my second derivative, I treat the first derivative like an original function, handcuff the peaks and valleys. My red function is decreasing, therefore the graph of the derivative is negative. The red function is increasing, graph of its derivative is positive, and that would be the second derivative. And again, if I did this right, this should go to the point of inflection on the original function, and it does. So this is something good that you want to keep handy to remind yourself. And in fact, I'm going to refer to this as we look at this question. Maybe we'll have to write our work somewhere else. So let's see what it says. It says, find the x-coordinate of each point on the graph of G, that G has a horizontal tangent line. So you guys remember, G is the original function. We're looking at the derivative. And in fact, just to stress this point that this is a derivative for this spot, and you may want to do this actually on your test, I'm actually going to overlap this in red. Now it doesn't show up very well, but it can kind of help you. And you can compare this to this right here. So you want to ask yourself, where does the original function have a horizontal tangent line? For each of these points, determine whether it's a max, a min, or neither. Now the one thing I didn't draw on this, which I'll do it over here kind of small, sometimes our original function doesn't have a peak or a valley, it has a flat spot. So let's pretend this would have happened. So let's pretend that as my function was increasing, I just had a flat spot, and then it did this. Okay? We'll do a quick little graph here. And so I have to do my second derivative. Well, I'm going to do my peak. I don't have a valley, but I do have a flat spot right here. Okay? And so if I have to graph my derivative, if you'll notice, the function is increasing the whole time. Therefore, what that tells me is that my graph of my derivative's got to be positive the whole time, but there's a 0 right there. So it's positive, but there's a little kiss right there. A little kiss, it still stays positive, and then it goes through. This was supposed to be handcuffed there, okay? Then it goes through, and that's the graph of my derivative, because this is my original function here. So the original function was increasing the whole time, therefore the graph of the derivative was positive, except for that one little 0. The original function was decreasing, graph of its derivative is negative. Now just to polish it off, we'll do the second derivative. So second derivative, I would say, well, I have a little peak right there, and I have a little valley right there that connects to itself. Okay, so the red function is decreasing, therefore the graph of the derivative is negative. The red function is increasing, therefore the graph of, got to draw my other handcuff here, therefore the graph of its derivative is positive. The graph of the derivative is negative, therefore the graph of this derivative is, the red function is decreasing, the graph of its derivative is negative. Okay, so let's see what's asking in the question, then we'll compare them to these two. So what it says here is find the x-coordinate of each point at which the original function has a horizontal tangent. Okay, well you can look here, horizontal tangent, and what happens? The derivative is crossing the x-axis. Horizontal tangent, we're crossing the x-axis or kissing. So what you guys want to do is go to this graph and say, is there any place where the graph of this derivative is crossing the axis or kissing? As you look at it, it should jump right out at you. And you should say, oh, well, it's definitely crossing right there. And it's kissing, not exactly a perfect kiss there, because it's not nice and smooth like it is here, but it's touching the x-axis right there. And so the first part of the question says, find the x-coordinate where the graph of G has a horizontal tangent. Well, it's at 1 and -1. And so actually, I'll fit this in right here. That way we can save our graphs over here. Okay. And so what I'm going to say is that there's horizontal tangents. Horizontal tangents at, we're going to say, at G prime of -1 and g prime of 1, which is the same as f of 1 and f of negative 1. So there's where we'd have horizontal tangents. Okay? So we've got that point, and then it says, say whether they're a max, a min, or neither. Well, let's take a look here. Notice that I had a maximum when my derivative was going positive to negative, a minimum when my derivative was going negative to positive, and I had a flat spot when I was kissing. So it looks like I have one kiss and one positive to negative. That sure looks like it'll be a maximum. So g of negative 1 is a maximum. So I would say g has a I'll sneak this in right here. G of 1 is equal to a max because g prime of 1 goes from positive to negative. Okay, that's what they want to know. What's the sign of g? So because g prime at 1, sorry, not g prime of 1, g prime of x, okay, goes from positive to negative. Just for neatness here, I'm going to go ahead and make the next line here. G prime of 1 is equal to a max because g prime of x goes from positive to negative at x is equal to 1. Okay, so my derivative is going from positive to negative. That had to make a max on g of 1. Okay, and then g of negative 1, let's see if we can figure this one out. So, sorry, I've had my numbers written backwards. This first one is the negative 1. Sorry for that confusion there. So g of negative 1 is the max. I was looking at it, but writing it down as 1. And so now the second one is, let's see if we can figure out what kind of kiss we have going on here. So it's just touching there. And so they just want to say in the question, is it a maximum, minimum, or neither? And g prime of 1 is equal to neither because g prime of x does not change sign at x is equal to 1. So there was 3 points here, and so we went over a lot of stuff here, so I want to recap this question here. So the question says, there's your derivative, find your maxes and mins, and this directly relates to your skills at understanding the graphs of derivatives. And so just to review this, I said, well, when we graph a derivative here, peaks and valleys of originals are intercepts on the graph of the derivative. And the one little curveball you can get is a flat spot makes a kiss. But notice how the x-axis is crossed or touched whenever your original function has a flat spot. Peaks cross, valleys cross, flat spots kiss. And so it said, identify where you have horizontal tangents. Well, there's only 2 spots you have the x-axis being touched, so it was negative 1 and 1. And then say what kind it was. Negative 1, positive to negative, so I must have had a max. G prime goes from positive to negative. And at g of 1, I had a kiss there, so it was neither, it wasn't a max or a min because the g prime didn't change sign. It stayed negative the whole time. Okay, so there's C. Now part D says, from negative 4 to 3, find all the values in which the graph of g has a point of inflection. Explain your reasoning. Okay, well, this is one of the reasons why I wanted to take the time to graph the blue, just to kind of show you here what's going on. So the point of inflection, there's a couple of ways to do this. I'm going to show you the easy way. As I look at this graph right here, I want you to focus on this one. I only had one point of inflection. And the point of inflection occurs, yes, when my second derivative hit the x-axis, but I want you to focus on the first derivative because that's what we have here. What's going on the first derivative when an inflection point is created? And the answer is your first derivative will change direction or change sign. Okay? And so my first derivative, or my second derivative, is changing sign at that spot, but which is the slope of the red. And so, but the easy way to identify them is look at your first derivative and look for any peaks or valleys or flat spots. In fact, let's go to this one now for that. If you'll notice on this one, I must have had a point of inflection around right here. You could see that I was concave down, and then right here it's concave up, and then it's concave down again. So right here and right here, I had 2 inflection points. So what that tells me is if we look closely at our derivative, my derivative, or the red graph, must have had a peak or a valley. Sure enough, there's the valley bottom, and sure enough, there's the peak. Okay, so do you want to see where you have inflection points? All you have to do is look for where the first derivative changed direction, which tells you your second derivative is changing sign. So here's how fast you can get it. As I look at this, it should jump out at you. You guys should say, oh, look at that. My first derivative is going from increasing to decreasing. There's going to be an inflection point on the original. Right down here, there's another change of direction. There's going to be an inflection point on the original. And then right here, there's my third one. I have 3 places where my derivative peaks or valleys here, which tells me my second derivative is changing sign. So I think I actually can sneak that in right here. We have room. So this would be part D. I'm going to sneak that in. It says, find all the values for which G has an inflection point, and then explain your answer. So even if you struggle with the explanation, you should be able to look at this and say G has a point of inflection at x is equal to, and we have 3 points. It is at -2. It's also happening at 0, and it's also happening at 1. We're going to explain our answer. And I'm just going to say because the second derivative, which is actually f prime, because f prime of x, which is equal to the second derivative of g, changes sign at these places. Changes sign at x equals -2, 0, and 1. Now, I know there are some students that you would like to take this and try to sketch your second derivative. I don't recommend doing that because this is not friendly. When you have those corners, and it's just a little bit ugly. You want to take advantage of the alternate way to get your inflection point, which is just when's the first derivative changing direction. Really, the first derivative tells you everything. And where it changes direction, where the first derivative is increasing, you can also see where my first derivative was increasing, my original function was concave up, where it was decreasing, it was concave down. But this is a really good graph to just have handy to just verify your values with. Okay, so that was 2012. Question number 3, derivative graph. Lots of stuff and some review concepts here. And first curveball was, might be the first time you've seen this, where the fundamental theorem was a little bit incomplete because they didn't use the other value because it was defined a little bit differently, which might have been weird. Had that but erased it. And then our second one was a pretty simple one. Read the graph. Third one for C, horizontal tangents, and a review of our graphs. So these right here are notes. This was not required. This was just to help explain our work. And then D, finding inflection points. Okay, so watch that as many times as it takes to go through those, and hopefully it'll sink in. And there's more of these to practice. But there it is, 2012, question 3, derivative graphs. All right, thanks for watching. We'll see you guys next time.